1202, Leonardo of Pisa, better known as Fibonacci, uncovered a link for merging the study of mathematics, nature, and art. Not only did Fibonacci introduce the Christian world to the Hindu-Arabic numerals we use today, but he also posed a seemingly innocuous problem about bunny rabbits. Fibonacci wanted to know how many rabbits would be produced in a year, beginning with a single pair. He assumed that starting in January and continuing every month thereafter, each pair of rabbits would bear a new pair once they were a month old. As he worked towards a solution, he noticed a pattern emerging. The number of rabbit couples increased in a certain sequence each month: 1, 2, 3, 5, 8, 13, 21, and so on. Each number in this series equals the sum of the two previous numbers. 3 plus 5 equals 8, 5 plus 8 equals 13, and so on. These numbers, growing to infinity, are known as the Fibonacci series. This may appear to be of little consequence, but these numbers would become the key to unlocking more mysteries than a plague of bunnies. For instance, in the field of botany, the structure of flowers is based on Fibonacci numbers. Lilies have a radial symmetry based on 3. Violets have 5 petals. Sunflowers have petals totaling 33, 55, or 89. This phenomenon, not explained until 1993, appears to go beyond genetics to the natural dynamics of growth. Whether it is the spiral of consecutive seeds in a sunflower, the spiraling growth of a chambered nautilus, or the branching structure of bronchi in the lungs, organic growth is often guided by a mathematical ratio stemming from the Fibonacci series. As Fibonacci numbers increase, the proportion of two successive numbers becomes more and more similar. The ratio approaches but never reaches an infinite decimal beginning with the numbers 1.618. This ratio was given the name the divine proportion and was later called the golden mean. Eventually, it was given the abbreviation phi after the initial of the Greek sculptor Phidias, creator of the artwork on the Parthenon. As early as the Pythagorean school in 500 BC, the Greeks studied the ratio of phi and developed a method of constructing a rectangle with sides measuring 1 and phi. With a perfect square, a line from the midpoint, and an arc, they created what was later called a golden rectangle. The Greeks also found that if they removed the original square, what was left was itself a golden rectangle. The Greeks believed that the golden rectangle held a mathematical key to beauty, and they incorporated it into many designs. The most striking example may be the Parthenon, with most of its proportions based on golden rectangles. The Greeks were not the first to use the visual balance of phi in their architecture. 5,000 years ago, the Egyptians based the design of the Great Pyramid of Cheops on golden proportions. This measurement may not have been intentional, but it reinforces the belief that phi holds some universal aesthetic appeal. For centuries, artists have studied the psychology of beauty, while biologists have sought to untangle the complexities of nature. Yet it was Fibonacci, an Italian mathematician 800 years ago, who found the common mathematical thread that connects these two disciplines and provides a deeper understanding.
The circumference of any circle is a little more than 3 times its diameter. In other words, the ratio of circumference to diameter is about 3.14, a fundamental constant of nature denoted by the Greek letter pi. The area of a circular disk is some number times the square of its radius. This factor A is another fundamental constant of nature. Surprise, it's the same number pi. To see why this is true, unwrap half the circumference for reference. Divide the disk into an even number of equal slices, and rearrange them to form a sort of parallelogram with the same area as the disk. As we take more and more slices, making them thinner and thinner, the parallelogram becomes more and more like a rectangle, with base pi r and altitude r, and the area is pi r squared. Here's another method. Divide the disk into concentric rings. Unwrap them and pile them up like this. As we take more and more rings, the stack looks more and more like a right triangle, with base 2 pi r and altitude r. Its area, 1/2 base times altitude, is pi r squared. The decimal digits of pi have no regularly repeating patterns. One of the most practical uses of supercomputers is calculating 1 billion digits of pi, a truly transcendental experience. Pi shows up whenever circles do, in formulas for areas and volumes of solids of revolution. But it also shows up in some problems where there are no circles at all. For example, drop a needle on a floor whose boards are twice as wide as the needle length. The needle might land on a line or it might not. Drop lots of needles. The probability that a needle crosses a line is 1/pi. The next example comes from number theory. Put a yellow dot at each lattice point whose rectangular coordinates have no prime factor in common. Another way of saying this is, put a yellow dot at each lattice point that's visible from the origin. The dark dots are hidden behind the bright ones. The probability that a lattice point is visible from the origin is 6/pi squared. Pi has something to do with prime numbers.
Several particles are walking on a square lattice. When a particle reaches a vertex, it can elect to go up, down, left, or right at random. Each particle behaves independently of all the others. As the number of particles grows, their center of gravity becomes more and more stable. Here we have 4 particles. The white ball is their center of gravity. Sixteen particles. Sixty-four particles. 256 particles. Several moving particles are trapped in a box. As they hit the sides of the box, or when 2 of them collide, they bounce off like balls in a game of billiards. In this situation, nothing is random. It is a deterministic dynamic system. Yet, when the number of particles grows, the system behaves as if the particles were randomly independent. Such a system is called ergodic. Again, the white particle is the center of gravity. Here, there are 16 particles. "64 particles. This phenomenon is essentially independent of the shape of the box. Here we have 4 particles. "16 particles. "64 particles.
Vehicle dynamics simulation plays a key role in modern car engineering. Virtual prototyping cuts product development time and cost. To realistically test drive vehicles in the computer, all parts of the vehicle must be simulated, including the suspension, powertrain, engine, and steering mechanism. The car and its components are described by mechanical systems interconnected by joints that can move or articulate in 3 dimensions. In the computer, the virtual prototype is described by a large number of differential equations. These equations can only be solved by using computational methods from numerical mathematics. Here, the red arrows at the wheels indicate the computed braking or accelerating forces. The blue arrows display the lateral forces acting on the car. A virtual prototype must be tested under various road conditions. Every maneuver normally run on a test track must be investigated in the computer. Road parameters, such as weather and road surface conditions, are easily controlled for virtual test drives. Thus, the handling characteristics and vehicle safety of the physical prototype can be predicted precisely. The ISO slalom test is a typical handling maneuver for passenger cars that tests road holding and safety. Here, we investigate the performance of a private car depending on a single parameter, the center of gravity. Test drives of cars in the computer avoid the risk of damaging both the human test driver and the physical prototype. The numerical simulation of test drives has very real benefits.
The simulation of flow phenomena and the understanding of the governing physical process is a challenging subject of ongoing research. Here the flow around a cylinder is shown in a physical experiment and in a comparable numerical simulation. In what follows, the numerical simulation of complex flow is shown in several applications. The supersonic flow in a channel with forward-facing step is a simple model for the flow in the inlets of supersonic aircrafts. Different shock patterns appear. From experiments, their location and shape is well known and can perfectly be reproduced by the simulation. Especially the vortex street, whose origin is the contact discontinuity, is an important flow feature. Modern numerical methods made it possible to reproduce this phenomena numerically. Another interesting engineering research topic is the study of gas exchange in a two-stroke engine. One looks for the optimal design of the burning chamber and the configuration of the inlets and outlets. Therefore, simulation of the compressible gas flow in a concrete geometry with moving piston, which temporarily opens and closes the inlets and outlets, is an important step in the optimal design process. Moving gas volumes visualize the engine's behavior. The aim is to design the engine such that no fresh gas, here indicated in blue, leaves the outlet before being burned. The evolution of particle clouds illustrates that this requirement is violated by the current geometry. The Van Karman vortex formation behind obstacles in an incompressible flow with high Reynolds number is a prominent flow pattern. Applying the new visualization approach of texture transport, the complex time-dependent flow can be analyzed. A closer look to the pressure, here indicated by colors, demonstrates that the minima of the pressure are situated in the vortex course.
Archimedes, considered the most important of the Greek mathematicians and of the whole of antiquity, lived in Syracuse, in Greater Greece, on the island known today as Sicily, in Italy. Many of the important discoveries in geometry made by Archimedes were achieved through the equivalence and equilibrium of physical models. We can imagine, for example, that he visualized a disk shape as being composed of concentric circles, extrapolating a model made with rope. By straightening the circles of rope, he could estimate and later prove that the area of a circle is equivalent to the area of a right-angled triangle whose longest side adjacent to the right angle is equal to the circumference of the circle, and whose shortest side adjacent to the right angle is equal to the radius of the circle. His ideas were so revolutionary that they influenced a large part of the mathematics still used today. Cavalieri, the disciple of Galileo and a professor at the University of Bologna, is famous for having set out, inspired by Archimedes, what came to be known as Cavalieri's principle. This principle is based on the conception of a flat area as a juxtaposition of infinite segments. Let's look at this rectangle made up of sticks. If we move any of these sticks, or segments, a new shape is produced, but the area remains the same. Cavalieri's principle states, therefore, that shapes which have transversal segments of the same length have the same area. Like these triangles, which are different from each other, but are formed from the same segments put together in different ways. They all have the same area. This principle also applies to the volume of solids, but here we no longer talk of length of segment, but rather of equal areas of plane sections. This is illustrated by this pyramid made up of slices. If we move these slices, we make a pyramid of a different shape, but the volume remains the same because the slices are the same, and therefore their areas are not altered. Cavalieri's principle was used brilliantly, yet intuitively, by Archimedes as a means of discovering the relationship between the volumes of a half-sphere, a cone, and a cylinder of the same base and the same height. Archimedes noticed that when we cut through the three solids at the same level, we obtain three slices, and the slice of the cylinder is always equal in area to the slices of the cone and the half-sphere together. He was inspired by the principle of physical equilibrium. Whatever sections are measured, the area and weight of the slices always balance. He concluded that the sum of the volumes of the half-sphere and the cone is equal to the volume of the cylinder. The volume of the cone is 1/3 of the volume of the cylinder, so the volume of the half-sphere can only be 2/3, which means that the ratio between the three volumes is of 3 to 2 to 1. It's easy to prove Archimedes' discovery in practice.
Geodesic curves are the shortest connections between 2 points. In the Euclidean plane, a rubber band contracts under the tension of the rubber molecules to a straight line which minimizes length. Geodesics are used in mathematics as a fundamental intrinsic concept in the study of surfaces and general manifolds. To find the shortest curves on Earth, we cannot take the straight line in space, but need to restrict all curves to lie on the sphere. Here, geodesics are segments of great arcs, paths which are taken by airplanes and ships. The boundary value problem for geodesics on general surfaces leads to different local minimizers, which all have minimal length compared with nearby curves. In a different interpretation, geodesics can be considered as the straightest curves on a surface. For example, when emanating a light particle in a certain direction, it will travel along the unique geodesic with the same initial point and direction, a property already noticed by Fermat in the 17th century. The straight line property of geodesics makes them a suitable concept also in numerics and visualization. For example, point waves on surfaces evolve through distant circles. The singularities of the wavefront are the conjugate points of the exponential map in geometry. The wavefront develops caustics at the conjugate points with the shape of a swallow's tail. For numerics, it is helpful to define discrete geodesics on polygonal surfaces. Planar faces are like Euclidean planes. The definition across an edge is an intermediate consequence, since both faces are isometric to a planar domain. The geodesic has equal angles at both sides of the edge. The situation at vertices is more delicate and uses the definition of discrete geodesic curvature of a curve. Light rays show a discontinuous behavior at the vertex. The situation can be better studied in a planar model. The light rays away from the vertex are straight lines, and the ray through the vertex bisects the total vertex angle. The definition of discrete curvature of curves allows an intrinsic description of curves similar to smooth surfaces. It uses the discrete Gauss curvature of a vertex. The normal vectors around a vertex enclose a patch on the unit's discrete Gauss curvature. A planar domain has zero curvature, and at a hyperbolic vertex, the patch changes orientation and has negative area. The total curvature of a discrete surface is concentrated at the isolated vertices. As a consequence, waves on discrete surfaces have singularities which are equivalent to those at conjugate points on smooth surfaces. Behind every vertex, there are three interfering waves, one from the left, one from the right, and a third segment generated at the vertex. The simulation of waves on surfaces and discrete geometries is an example of the use of intrinsic geometric properties in numerical integration of differential equations and the visualization of flows on surfaces.
Knot theory tries to detect when knots are equivalent, but it is hard to tell how to simplify a complicated knot like this. One approach is to associate an energy to every closed curve in space and evolve the curve to reduce this energy. For instance, if we spread electric charge along the curve, minimizing the potential energy would make the strands repel each other. We use a renormalized double integral over pairs of points on the curve of 1 over distance squared. The computer models this experimentally with polygonal curves. Since our starting curve was an unknot, though quite tangled, it evolves to the round circle, which has the minimum possible energy for any curve. The simplest truly knotted knot is a trefoil or overhand knot. Minimizing its energy, we get a symmetric curve, also constructible theoretically. Rewinding, we can watch the evolution again to see how three-dimensional the curve becomes. The minimizing configuration is a 2-3 curve on the surface of a round torus. Our knot energy is Möbius invariant, so as we take a tour through the conformal group, all of these are equivalent energy-minimizing trefoils. As we change the conformal view, sometimes we see twofold or threefold Euclidean symmetry. The curve actually has a continuous Möbius symmetry. It is the orbit of a point under a rigid rotation of the three-sphere. The 3-4 torus knot evolves first towards a but this seems unstable, and eventually the symmetry gets broken. We reach the presumed minimum with energy about 1% less. Rewinding, we can watch the evolution again. Similarly, the 3-5 torus knot has a symmetric configuration on the surface of a round torus, but this seems unstable and evolves to break its symmetry. This connected sum of two trefoils degenerates under energy minimization. In the limit, it has just twice the energy of a minimizing trefoil, since the two pieces hardly interact. It is known that all prime knots have minimizing configurations. Here, conformal transformations could keep one of the two trefoils from shrinking, but not both at once. Two distinct 10-crossing diagrams, which represent the same knot, the so-called Perko pair, evolve to what seem like distinct minima. But in fact, these curves are Möbius equivalent. Our energy also works for links like the Borromean rings. By Möbius invariance, this energy-minimizing configuration has various forms, including 3 ovals in perpendicular planes.
Now let's have a look at some minimum energy models, that is, providing maximum stability for given shapes. This is what we obtain by immersing a cubic form in the soap film. And this is what we get with a tetrahedral form, with a bubble at the center of the structure. The color depends on the thickness of the film and the type of soap used, as Boyce observed at the beginning of the century in a classic work on soap bubbles. If we use a dodecahedral form, we get an incredible number of soap films inside the structure, which create extraordinary light effects.
In the 3rd century BC, the Greek astronomer and mathematician Eratosthenes was able to estimate the size of the Earth with surprising accuracy. Eratosthenes was the director of the Great Library of Alexandria in northern Egypt. In one of the papyrus scrolls in this library, he read an account from Siene in southern Egypt. It was observed that on June 21st, the longest day of the year, vertical objects cast no shadows. As the sun approached midday, the shadows from the temple columns grew shorter and shorter until they were entirely gone. In addition, the reflection of the sun could be seen in the water of a deep well. All this indicated that at that moment the sun was directly overhead. Eratosthenes tried to reproduce these results in Alexandria on June 21st and found that there vertical objects did cast shadows at noon. From this discrepancy, he concluded that the Earth must be curved. He first reasoned that the sun shone light on Siene angle. Since the sun is so far away, only the light that is aimed directly at Earth will reach our relatively small planet. This specifically aimed light hits all of the Earth from essentially the same angle and can be considered parallel. Eratosthenes then imagined 2 columns of the same height, one at Alexandria and one at Siene. If at any moment neither column cast a shadow, the sun must be directly overhead both, hitting them at the same angle. Even if they cast shadows of equal length, the sun would be shining on the right angle, formed by the columns in the ground, from the same inclination, a scenario only possible on a flat Earth. However, this was not the case. For the parallel rays of sun to be hitting the columns at different angles, the surface of the Earth must be curved. Eratosthenes reasoned that the greater the difference in shadow length, the greater the curvature of the Earth. From the length of the shadow and the height of the column, Eratosthenes calculated that in Alexandria on June 21st, the sun was shining at an angle of 7 degrees. Using Euclid's geometry of parallel lines, he deduced that if the columns at Alexandria and Siene were continued underground, they would eventually meet at the exact center of the Earth at an angle of 7 degrees. Since the 2 cities were 7 degrees apart on the sphere of the Earth, the distance between them was about 1/50th the distance around the whole Earth. Eratosthenes hired a man to walk from Alexandria to Siene and count his steps. This measurement showed the distance to be approximately 800 kilometers. With 7 degrees around the Earth measuring 800 kilometers, Eratosthenes calculated that a full 360-degree circumnavigation of the Earth would measure approximately 40,000 kilometers. This measurement, which is only 800 kilometers less than the Earth's true circumference, was made with simple observations and basic geometry nearly 17 centuries before the age of exploration and the first concise global maps.
The theorem of Pythagoras is one of the oldest results in all of mathematics. In any right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. In other words, the sum of the areas of the 2 small blue squares is equal to the area of the large one. To see why, make 4 copies of the right triangle. Put this here for reference. Now slide the triangles around and just keep track of the areas of the blue regions. And we see that a squared plus b squared is always equal to c squared. Here's another proof. The area of this green region doesn't change if we shear, rotate, and shear again. The same is true for this blue region. And again, we see that a squared plus b squared is indeed equal to c squared. Still not convinced? Cut a copy of the small square in the middle of the large square. Make cuts out to the edges. And here's yet another proof. Divide the triangle into 2 similar right triangles. The area of the big one is the sum of the areas of the 2 smaller ones. Because the areas of similar figures are proportional to the squares of the length of the edges, we get the Pythagorean theorem. Once again, instead of squares or triangles, you can put any three similar shapes on the sides of a right triangle. The sum of the areas of the two smaller shapes is equal to the area of the large one. To extend the theorem to 3 dimensions, we use the two-dimensional theorem twice. There's one right triangle on the floor and another perpendicular to the floor. The square of the diagonal of a rectangular box is the sum of the squares of the 3 perpendicular edges.
An eversion turns a sphere inside out without ripping or pinching. However, the surface is allowed to pass through itself. Our sphere eversion differs from earlier ones. It is computed automatically by minimizing elastic bending energy. The computer uses polyhedral approximations, adaptively updating the triangulation. The sphere, with its 2 sides painted yellow to red and blue to purple, increases energy as it contorts itself into the symmetric halfway stage. Then, it relaxes down again to a round sphere. The minimax eversion constitutes an optimal route over the lowest saddle for the bending energy. The computation begins with this immersed sphere, whose 4-fold symmetry interchanges inside and out. Using second-order information about the energy, we push off the saddle and we proceed downhill by gradient descent. When the North Pole pushes past the South Pole, the sphere ceases to be embedded, and the first double curve is born. Lobes near the neck form a second double curve. Arcs converge to spawn 4 triple points, the corners of a tetrahedron, which shrinks to the quadruple point. On the other side of the energy saddle, the triple points disappear in pairs, and the double curves shrink and vanish. The whole process is inverted in time with a 90-degree twist. At all times, the everting sphere maintains a 2-fold rotational symmetry. A tangency of 2 surface patches creates, annihilates, or reconnects the double curve. This reconnection was called the isthmus point in the computer animation classic Max. 4 additional reconnections happen at the so-called ears. At the halfway stage, 2 ears open just as the other 2 are closing. When 3 surface patches meet along a common tangent line, a pair of triple points is born or dies. 4 surface patches cross at a quadruple point. A Morin surface is an elaborately immersed sphere whose pleasing 4-fold symmetry reverses orientation, interchanging the orange and blue sides. This halfway model is a Morin surface of least Willmore bending energy. Willmore's energy is invariant under the Möbius group, so that any of these conformally equivalent surfaces could have been our halfway model. When the quadruple point reaches infinity, we have Kussner's minimal surface with this explicit Weierstrass representation. Kussner's surface has 4 flat ends, which cut the sphere at infinity in a cube-octahedral pattern. Continuing our conformal tour, we send the isthmus point to infinity so that the surface now has 2 wavy ends with a quadruple point at the center. To avert a sphere, it suffices to describe a regular homotopy from the halfway model to the round sphere. Morin classified the simplest of these homotopies. Brackey's computer program, the evolver, automatically finds one of these strategies purely by minimizing bending energy. This triangulated cube octahedron was everted by Apéry and Denner. Their halfway model is a polyhedral Morin surface. Relaxing it in the evolver, keeping the symmetry, we descend to the Minimax halfway model. The Minimax principle applies to all eversions in an infinite sequence with increasing rotational symmetry, called the tobacco pouch eversions. Those of even symmetry, like this order 4 example, generalize Morin's eversion. Their halfway models reverse orientation by a rotational symmetry. The eversions of odd symmetry use doubly covered projective planes at the halfway stage. This order 3 eversion passes through Boy's surface, an immersed projective plane with threefold symmetry and a single triple point. Converging to Boy's surface, two oppositely oriented sheets overlap and compete to show their orange and blue colors, accounting for the twinkling facets. Then, Boy's propeller-shaped double curve splits into its fourfold covering, and a cube grows from the sextuple point. Our ensemble of spheres now join in performing eversions with 2, 3, 4, and 5-fold symmetry.
This demonstration shows virtual creatures that were evolved to perform specific tasks in simulated physical environments. Swimming speed was used to determine survival. Most of the creatures are results from independent evolutions. Some developed strategies similar to those in real life. Once they're evolved, multiple copies of these creatures can be made and simulated together in the same environment. The next group of creatures were evolved for their ability to move on a land environment with gravity and friction. Some simple solutions with just 2 parts were found. Some seemed like they could use some assistance, while others were fairly efficient, such as this rowing-like behavior. Here is an odd cousin of the previous. A mutation caused him to tumble instead. Some creatures evolved to incorporate contact sensors in their control systems. Here is another inchworm-like creature that tends to go in circles. This was actually a creature first evolved for its ability to swim in water, then later put on land and evolved further. A successful sidewinding ability resulted. Here is one with a hopping style. The protrusions on its arms seemed to help prevent it from tipping over. This was the fastest, with a successful galloping-like stride. This group was evolved for their jumping ability. This group was evolved for their ability to adaptively follow a red light source. The resulting creatures are now being interacted with. A user is moving the light source around as the creature behaves. This one seems to flail randomly, but somehow still manages to approach the light. Perhaps it is mean to move the goal away just as it arrives. Here is one that has propeller-like fins which are tilted depending on the direction of the light. It can adaptively swim up or down very well. This final group of creatures was evolved for their ability to compete for control of a green cube. The creature closest to the cube at the end of a simulation is the winner. Here, a strategy first arose for simply tumbling towards the cube. Then one learned to block out his opponent. But then later one learned to overcome the obstacle by climbing over it. Some pinned down their opponents. Some covered the cube with protective arms. Others simply unfolded onto the cube. The success of a strategy is often highly dependent on the opponent. Here is a hockey-playing creature, which takes the cube away and wins by a large margin. Here are 2 similar hockey strategies battling it out, with appropriate gestures. This crab-like creature walks well, but often continues past the cube and instead seems to prefer beating up on his opponent. Against the arm, the crab seems to simply walk away. A successful strategy is this 2-arm technique that swipes quickly in from the side and moves the cube over to a second arm. These are the final rounds of competition amongst the overall best. Finally, the seeker arm goes against the side swiper, but the cube is just out of reach. A new machine developed in our lab allows the interactive modeling and deformation of complex, smooth shapes and hierarchical control of level of detail and curvature. In this animation, we use this representation to illustrate a mapping which used topologists to point out differences between 3 compared to 2-dimensional spaces. The objective of this mapping is to deform a sphere into an object without an interior. The deformation has only one rule. The surface is not allowed to fall directly back into itself or to have any self-intersection. For example, squishing the sphere into a flat disk violates this rule. In contrast, Bing's construction shows a smooth deformation with no self-intersection that retains smoothness until the last step. Let's repeat Bing's deformation sequence and add transparency to see the interior. Notice how the sphere is traversed by two arm-like appendices that reach around one another to form two chambers. These chambers form a house. Each chamber is accessed by a tunnel that crosses the other. We need this intricate interweaving to not have the surface fall back on itself.
Have you ever wondered how big the universe is? How many stars are there? Does space go on forever? The answer depends on the shape of space. Let's explore some possibilities. There's an interesting star. This star looks familiar. Haven't we been here before? What's going on? What kind of space is this where we keep seeing the same stars again and again? It's easier to explain in a two-dimensional universe than a 3D one. But what would a 2D universe be like? Let's call it flatland. Life in two dimensions has its problems. When two flatlanders want to pass one another, they can't go around each other or to the side as we would, since they can't leave the plane. Our athletic flatlanders must jump over one another to continue on their way. The flatlanders live on the one-dimensional surface of our planet, just as we spacelanders live on the 2D surface of our 3D planet. The flatlanders' planet is orbiting a sun. Their sun is a two-dimensional disk, just as our sun is a three-dimensional ball. Like ours, their sun is just one of many stars in their universe. Let's watch the flatlanders explore their universe. Straight off into space and are surprised to come across their own sun. Perhaps their universe is a sphere and they took a trip around its equator. Or perhaps it's a cylinder. Or a torus. Each of these surfaces is a possible shape for a two-dimensional universe. Suppose their universe is a torus. We'll save a copy of it, cut the torus once, and deform it into a cylinder. Cut it again, and open it into a square. This square is a fundamental domain for the Flatlanders' universe. We now see their universe using only two dimensions. The Flatlanders can still travel about their universe as before. When looking at a fundamental domain, we must imagine that its edges are glued together. Anything leaving one glued edge returns at the other. The way we glue them determines the shape of the space. What do the Flatlanders see in this universe? Their line of sight travels around the universe, and they see the back of their own spaceship. Like the Flatlanders themselves, their line of sight can't leave their two-dimensional space. They see what appears to be a copy of themselves. Indeed, they see images of themselves in many directions. This tiled picture shows what the Flatlanders see, and that their universe is boundless. They'll never reach an edge. From the picture of the single fundamental domain, we see that their universe is not infinitely large. It contains only 3 stars and 1 spaceship. It's finite. Neither picture alone gives the full story. By combining these two pictures in your mind, you can get a better understanding of the true nature of their space. Now we're ready for 3 dimensions. Take a cubical block of space. We'll use this for our fundamental domain in 3 dimensions, just as we used a square in 2D. We glue the left and right walls. Now the spaceship can travel around this finite universe, passing the same stars again and again. We glue the top and bottom. And finally glue the back to the front. Now the space has no boundary and the ship can travel in any direction. This space is called a 3 torus. Let's ride the spaceship inside the 3 torus. Even though the 3 torus is finite, we have the illusion of flying in an infinite space. There are only 2 stars in this universe, but we see each one over and over. This isn't the only possible shape for space. 2 pairs of faces connect as in the 3 torus. To make the flip, connect the top of the right face to the bottom of the left face and vice versa. After 1 trip, the spaceship appears mirror reversed. After a 2nd trip, it returns to its original state. Let's see what this space looks like from the inside. As in 2D, we see infinitely many images of our ship. Half are mirror reversed, half are not. When we roll, our reversed images roll in the opposite direction. Life in this space is different than in the 3 torus, where all the copies of the ship move in the same direction, like a flock of birds. We fly this way and see ships in neighboring rows flying in the opposite direction. The mirrored images turn as we do to fly along paths that seem to cross ours, but they can never hit us. That's impossible in this space. We've looked at only a few of the many possible shapes for space. There are other ways to glue the walls of a cube together. Or instead of a cube, we could use a different shape for the fundamental domain. The space we saw at the beginning of this video was really a 3 torus, containing only 96 stars. This space is finite, but boundless. Astronomers face similar possibilities as they try to understand the real universe we live in, whose shape is still unknown. It is much larger than the simple spaces we've seen in the video and contains vast numbers of stars. But the same principle applies. What seems to be a star in a distant galaxy could be our own sun. The light we receive from it could be light which left the sun billions of years ago, traveled around the universe, and is just now completing its trip. If we can someday find a pattern in the arrangement of the galaxies, then we will know the true shape of space.